Welcome back, students. Our objectives for the day: discuss the factors that disturb equilibrium, discuss conditions under which reactions go to completion, describe the common ion effect. Predicting the direction of shift. Changes in pressure, concentration, or temperature can alter the equilibrium position and thereby change the relative amounts of reactants and products. Le Chatelier's principle states that if a system at equilibrium is subjected to a stress, the equilibrium is shifted in the direction that tends to relieve the stress. This principle is true for all dynamic equilibria, chemical as well as physical. Changes in pressure, concentration, and temperature illustrate Le Chatelier's principle. Changes in pressure. A change in pressure affects only equilibrium systems in which gases are involved. For changes in pressure to affect the system, the total number of moles of gas on the left side of the equation must be different from the total number of moles of gases on the right side of the equation. An increase in pressure is an applied stress. It causes an increase in the concentrations of all species. The system can reduce the total pressure only by reducing the number of molecules. The Haber process for the synthesis of ammonia is depicted here. Notice that we have 4 molecules, or 4 moles worth of gas on one side, and 2 molecules, or we could say 2 moles worth of gas on the right-hand side. When pressure is applied, the equilibrium will shift to the right to produce more NH3, hence fewer molecules of gas. By shifting to the right, the system can reduce the total number of molecules, which leads to a decrease in pressure. Even though changes in pressure may shift the equilibrium position, they do not affect the value of the equilibrium constant. The introduction of an inert gas such as helium into a reaction vessel increases the total pressure in the vessel, but it does not change the partial pressures of the reaction gases present. Increasing partial pressure, or increasing pressure by adding a gas that is not a reactant or a product, cannot affect the equilibrium position of the reaction system. Changes in concentration. An increase in the concentration of a reactant is a stress on the equilibrium system. An increase in the concentration of A creates a stress. To relieve the stress, some of the added A reacts with the B to form products C and D. The equilibrium is reestablished with a higher concentration of A than before the addition and a lower concentration of B. Changes in concentration have no effect on the value of the equilibrium constant. Such changes have an equal effect on the numerator and the denominator of the equilibrium expression. The concentrations of pure solids and liquids do not change and are not written in the equilibrium expression. When a solvent such as water, in a system involving acids and bases, is in an equilibrium equation, it is not included in the equilibrium expression. High pressure here, if we increase the pressure here, a high pressure favors the reverse reaction. A low pressure favors the formation of CO2. Because both CaO and CaCO3 are solids, changing their amounts will not change the equilibrium concentration of carbon dioxide. Changes in temperature. Reversible reactions are exothermic in one direction and endothermic in the other. The effect of changing the temperature of an equilibrium mixture depends on which of the opposing reactions is endothermic and which is exothermic. The addition of energy in the form of heat shifts the equilibrium so that energy is absorbed. This favors the endothermic reaction. The removal of energy favors the exothermic reaction. A rise in temperature increases the rate of any reaction. In an equilibrium system, the rates of the opposing reactions are raised unequally because we have an endothermic side and an exothermic side. This means the value of the equilibrium constant for a given system is affected by temperature. This is the only thing that really will affect the equilibrium constant. The synthesis of ammonia by the Haber process is exothermic. A high temperature favors the decomposition of ammonia, in other words, towards those reactants, the endothermic reaction. At low temperatures, the forward reaction is too slow to be commercially usable. The temperature used represents a compromise between kinetic and equilibrium requirements. We tend to do it at a very high temperature, but also very high pressure. Catalysts have no effect on relative equilibrium amounts. They only affect the rates at which equilibrium is reached. Catalysts increase the rates of forward and reverse reactions in a system by equal factors. Therefore, they do not affect K. Reactions that go to completion. Some reactions involving compounds, formed by the chemical interaction of ions in solutions, appear to go to completion in the sense that the ions are almost completely removed from solution. The extent to which reacting ions are removed from solution depends on the solubility of the compound formed and, if the compound is soluble, on the degree of ionization, formation of a gas. This reaction goes practically to completion because one of the products, CO2, escapes as a gas if the container is open to the air. Formation of a precipitate. If chemically equivalent amounts of the two solutes are mixed, almost all of the silver ions and chloride ions combine and separate from the solution as a precipitate of silver chloride. Silver chloride is only sparingly soluble in water, and the reaction thus effectively goes to completion because an essentially insoluble product is formed. Formation of a slightly ionized product. Neutralization reactions between hydronium ions from aqueous acids and OH or hydroxide ions from aqueous bases result in the formation of water molecules, which are only slightly ionized. Hydronium ions and hydroxide ions are almost completely or entirely removed from the solution. The reaction effectively runs to completion because the product is only slightly ionized. The common ion effect. The phenomenon in which the addition of an ion common to two solutes brings about precipitation or reduced ionization is an example of the common ion effect. For example, hydrogen chloride gas is bubbled into a saturated solution of sodium chloride. We're adding extra chlorine, which is going to drive the reaction one way or the other. As the hydrogen chloride dissolves in sufficient quantity, it increases the concentration of chloride ions in the solution, which is a stress on the equilibrium system. The system can compensate by forming some solid NaCl. The NaCl precipitates out, relieving the stress of the added chloride. The new equilibrium has a greater concentration of chloride ions, but a decreased concentration of sodium ions. This is a representation of the particle model. We have the barium ions, the sulfate ions. Over here we have some sodium sulfate being added to it, and so that sodium sulfate, the sulfate is a common ion to both. It is going to pretty much guarantee you won't have any free-floating barium ions. The common ion effect is also observed when one ion species of a weak electrolyte is added in excess to a solution. Small additions of sodium acetate to a solution containing acetic acid increase the acetate ion concentration. The equilibrium then shifts in the direction that uses up some of the acetate ions. More molecules of acetic acid are formed, and the concentration of hydronium ions is reduced. In general, the addition of a salt with an ion common to the solution of a weak electrolyte reduces the ionization of the electrolyte. Well, that concludes this section. Please write down any questions you have, and I look forward to seeing you in class soon. Thank you, and goodbye.